Okay, so today we're going to look at the exponent laws. We're going to go through this table, fill it out, and then we're going to do some examples of exponent laws. So first exponent law is a product of powers. Now a power, this is a power. It has a base, which is 7, and it has an exponent, and the whole thing together is called a power. So here, let's clean this up. So if we have this power, 7 cubed times 7 squared, think about what that means. 7 cubed is 7 times 7 times 7 times, this times 7 squared. So this is 7 cubed, this is 7 squared. Multiplication is commutative. We can remove the brackets. We have 1, 2, 3, 4, 5 sevens, and the way we write that is 7 to the power 5. So when we multiply powers of the same base, we add the exponents, but the base remains the same. Okay, so we do not change the base remains the same. Expressing this in general, a to the m times a to the m is a to the power of m plus n. And an example using the rule, 3 to the 4th plus 3 to the 5th is 3 to the 4 plus 5, which is equal to 3 to the 9. Okay, moving down. Quotient of powers. Quotient is the division operation. 8 7 divided by 8 cubed is 8 to the 7th over 8 cubed. 8 to the 7th is the product of 7 eighths divided by 8 cubed. We can cross these off. When we do, we put 1's down. So 1, 1, and cross this one off. And we are left with 4 eighths, the product of 4 eighths, which is 8 to the 4th. When we divide powers of the same base, we subtract the exponents. But the base remains the same. Which should be written up here, the same. A to the m divided by a to the n is a to the m minus n. This is 6 to the 12 minus 8, which is 6 to the power of 4. Power of a power. So we take a power, raise it to an exponent. That's called power of a power. This means cubing 5 to the 4th. So it's 5 to the 4th times 5 to the 4th times 5 to the 4th. Using the product rule, which says when you're multiplying, you add the exponents. We get 4 plus 4 plus 4. There's 3 of these. What's the fast way to get a 12? It's 4 times 3. When raising a power to an exponent, we multiply the exponents. Multiply. But the base remains the same. I should be like capturing that and just pasting it in here, but the base remains the same. A to the m times a to the n is a to the m times n. That little dot. 2 to the 5th times 2 cubed is 2 to the 5 times 3, which is 2 to the power of 15. Power of a product. So that means we have here a product. 4 times 2, that's what's being cubed. So we want to cube that, right? We get 4 times 2 times 4 times 2 times 4 times 2. Multiplication, again, we do this in any order, so it's 4 times 4 times 4 times 2 times 2 times 2, or 4 cubed times 2 cubed. So when we raise a product to an exponent, we raise each, I'm going to say number or variable. Variable, that's what that word is, to the in the product to an exponent, and then multiply the powers. Basically each thing that's in here, right? Because it may not always be 2 numbers, as we could see in this example. So this, we separately take a to the power of m and multiply that by b to the power of m. So this becomes 3 to the power of 4 and a to the power of 4. So remember, this is a 3 to the 1 and an a to the 1. power to a power, we multiply exponents, right? It's just like here, power of a power. So it's 3 to the 1 times 4, a to the 1 times 4. Most people often forget this. They'll write 3a to the 4th. Really, that's 81a to the 4th, right? Okay, quotient. So power is, we have a multiply, quotients, we have a divide, 2/5. Cubed, 2/5 times 2/5 times 2/5. Writing like this, and then in exponential form, we have 2 cubed over 5 cubed. So when we raise a quotient to an exponent, we raise the numerator to the exponent, right? Numerator being the top number, and raise the denominator, to the exponent, and then divide the two powers. So this is a to the m divided by b to the m, in this case here, 3 to the 5 over 4 to the 5. Zero exponent. All right, where are we going to get a zero exponent from? Well, let's take a look at this. What if we have 8 cubed divided by 8 cubed, which looks like this, right, when written as a quotient, 8 cubed over 8 cubed, which is 8 times 8 times 8 over 8 times 8 times 8. Each of these guys cancels, right? Leaving us with a 1. So that's 1 times 1 times 1 over 1 times 1 times 1, which is 1. If we use the quotient rule, 8 cubed divided by 8 cubed is 8 to the 3 minus 3. That's 8 to the 0. Then these two things, 8 to the 0 and 1, must be equal to each other. And that means if the exponent of a power is 0, then the value of the power is 1 as long as the base of the power is not 0, right? We can't do 0 to the 0. So a to the 0 is 1 as long as a is not equal to 0. So 3,745 to the 0 is 1. And wow, that's a messy one. And sometimes, clean. Okay, there, nice and clean. Sometimes we'll get a really complicated expression raised to the 0, and if you recognize that, you can look and say, well, there's this big complicated expression, but since it's to the power 0, it's just going to be equal to 1. All right, if we do kind of the same idea here, but what if we take 8 cubed divided by 8 to the 7th? Right, so this, there's like 3 of these gone, and they're 1s, and there's 3 of these gone. So that leaves us 4 on the bottom. It's 1 over 4/8, 1 over 8 to the 4th. Now that's looking at it as multiplication, right? If we use the quotient of powers, 8 cubed divided by 8 to the 7th is 8 to the power of 3 minus 7 is 8 to the power of negative 4. So a negative exponent, 8 to the negative 4, is the same as 1 over the same base, 8, but to a positive exponent. So base raised to a negative exponent is equal to the base raised, the reciprocal of the base raised to the positive exponent, as long as the base of the power is not 0. So the reciprocal a to the negative n is 1 over a to the n. 5 to the negative 4th is 1 over 5 to the 4th. And of course each of these are evaluable, right? I mean, one you can do 5 to the 4th, you can work this out. So we could simplify these, right, and get like 243 over 1024, or whatever that is. This would be an 81, this would be a pretty big number, as would this, and so on, right? And we're just leaving them in this form here. Okay, we're going to move on. We're going to go, oops, that was the exponent laws table. We're going to go to the exponent law examples. And we're going to leave the bottom of the worksheet, the fractional exponent. We'll leave that for another day when we look more carefully at fractional exponents. Okay, evaluate without the use of a calculator first, and then check your answers with the calculator. So negative 3, now notice the base is in parentheses, so this means negative 3 times negative 3 times negative 3 times negative 3, right? In other words, 4 times. It's negative 3 times negative 3 times negative 3 times negative 3. So that, negative 3 times negative 3 is 9, times negative 3 is negative 27, times negative 3 is positive 81. This is the negative of 3 to the 4th. If you remember BEDMAS, right, brackets, so do the exponent first. 3 to the 4th is 81, and then take the negative of that. So that's negative 81. This is really the same as this as far as things go. When we have that negative in front, right, we have to do the exponent first. So this is negative 81. Try them in your calculator. Just make sure that you're enclosing this in parentheses, right? I'm going to pause, bring up a calculator. Okay, here's my calculator. Let's turn that on. Let's clear this. So I'm going to go bracket negative 3, close bracket, to the power of 4, hit enter, 81. Negative bracket 3 bracket to the power of 4, negative 81. Negative 3 to the power of 4, again, negative 81. Now remember, zero exponent, let's get rid of that. So a zero exponent is 1, so we have negative 5 to the 0. Anything to the 0 is 1. This is the negative of 5 to the 0, so this will be negative 1, and this is also, these two really are the same, right? Whether there's brackets or not, you're still going to do the exponent first, so negative 1. Negative 2 cubed is negative 2 times negative 2 times negative 2, so that is the negative 8. The negative of 2 cubed is negative 8, and negative 2 cubed is negative 8. Can brackets affect the value of a power? Yes. Okay, so especially if we have a negative value raised to an even exponent, we're going to get a positive answer. A negative value raised to an odd exponent will give us a negative answer here. Okay, let's move along. State whether each of the following statements is true or false. If the statement is false, write a correct statement. Okay, we have the product of powers. Product of powers, we are to add the exponents. This is false. The correct statement is 3 to the 5th times 3 cubed is 3 to the power of 5 plus 3. Okay, when you multiply powers with the same base, you add the exponents, the base remains the same, and that's 3 to the power of 8. When you multiply powers with the same base, you add the exponents, but you don't change the base, so this is false. 2 to the 5th times 2 to the 6th is 2 to the 5 plus 6, which is 2 to the 11. And, okay, 5. Now remember, 5 is 5 to the power 1. I just made a hash of that. Let's clean that up. 5 to the power 1. When you multiply powers with the same base, you add the exponents. 1 plus 6 is 7. True dat. This, wow, whoever is keying this for me has no idea how to do this stuff. Anyways. This, we have powers with different bases, so we cannot add powers, we cannot multiply these two together. This does not mean 5 times 4 cubed. This is false. The only statement we can get out of that is 5 cubed times 4 cubed. There's nothing you can do to simplify that. You may not multiply the bases because the powers are the same. Okay? You can only do stuff with powers when the bases are the same, in which case you end up with the same base, right? Okay. The negative of 3 to the 5th times the negative of 3 to the 8th. So what's going to happen is this result, remember we're going to do 3 to the 5th and then make it negative. We're going to do 3 to the 8th and then make it negative. And so we will have the product of two negatives. So this will not be a negative. So that is false. Okay, so we can think of this as negative 3 to the 5th. How do I want to write this? Here's what I'm going to do. I'm going to clear that out. I'm going to separate things out, right? So it's negative 1 times 3 to the 5th times negative 1 times 3 to the 8th. Negative 1 times negative 1 is 1, giving us 3 to the 5th times 3 to the 8th, which is 3 to the 5 plus 8, which is 3 to the 13. When we divide powers with the same base, we subtract the exponents, so that is true. Right? It's 6 to the 7 minus 2, which is 6 to the 5. Power to a power we multiply, so that is false. 5 cubed. Cubed is equal to 5 to the 3 times, that's supposed to be a times there, asterisk, times 3, which is 5 to the 9th. Okay, express as a single power with a positive exponent, and then evaluate. Well, the base is negative 2. The bases are the same, right? We can't multiply base of negative 2 with if this were positive 2. So the bases need to be the same. Bases are the same. We multiply. We add the exponent. So that's negative 2 to the power of 10. When you raise a negative to an even exponent, it'll end up as positive. So evaluating this, we get to the same as 2 to the 10th, basically, or 1,024. I'm firing my TA. I'm not getting very good results out of this. 7 to the 12th divided by 7 to the 10th, right? So that's 7 to the 12th over 7 to the 10th. You don't have to write this. We just have to recognize that this is 7 to the 12 minus 10, which is 7 squared, which is 49. Okay, power to a power you multiply. So this will be 3 to the 6th times 3 to the 8th over 3 to the 9th, which is 3. Okay, these powers have the same base. We add 3 to the 14th over 3 to the 9th is 3 to the 14 minus 9, which is 3 to the 5th, which is 243. Okay, and that's the and then evaluate. Write 5 to the 10th as a product of two powers. So as a product, it's got to be two things where the exponents will add to 10. So there's a lot of ways to do this, but here's one. 5 cubed times 5 to the, now what? Well, what with 3 adds to give you 10, 5 to the 7th. It's a product of three powers, so we need three numbers that are going to add to 10. So let's do 5 squared, 5 cubed, that's going to give me 5, right? It's power 2 plus 3 is 5. We're going to need another 5 to get to 5 to the 10th. Now, you know, your mileage may vary. You might have different answers for this, of course. As a quotient of two powers, 5 to the, stick with 5 to the 21. So we need two numbers that have a difference of 10, 21 minus 11. And this could have been written as a division statement like this, 5 to the 11. Power to a power, about 5 to the 5th. Now I need two numbers that multiply to 10, so 5 to the 5th squared, right? Or, you know, you could have done 5 squared to the 5th. Would have been hard. You couldn't do a 3 here, right? Because then, well, not yet you couldn't, but at some point we will. Okay, which is larger, 3 to the 444 or 4 to the 333, and justify your answer. Which is larger, 3 to the 444 or 4 to the 333? Go ahead, plug them into your calculator and see what happens. Oh, wait. No answers, huh? Now we got to think about it. So, here's the answer. 3 to the 444 is larger for a couple of reasons. 1, the exponent makes the bigger difference here than the base, especially when the bases are close. These numbers are very close. 3 and 4 are very close. So the exponent in this case dominates. So the larger exponent is going to make this difference. So 1, larger exponent. Exponent when the bases are close. Well, actually, that's pretty much the reason. So the larger exponent dominates when the bases are close. And we're going to move on. Negative integral exponents. So exponents that are negative and integral, or negative integers. So if 3 to the negative 2 is 1 over 3 squared, then what is the value of 1 over 3 to the negative 2? Okay, you can use your calculator to check that out. And you will find that you get 9. Here, shall we use the calculator? Let's clear. 1 divided by 3 to the power of negative 2 is positive 9. So in general, we know that if x to the negative m is 1 over x to the m, then 1 over x to the negative m is equal to x to the positive m. So the way I think about it is just wherever the negative is, put it where it isn't. So if it is on top, then you make it positive and put it on the bottom. If it's on the bottom, a negative exponent becomes positive, ends up on top. Express each power with a positive exponent and then evaluate. So that's 1 over 8 squared, which is 1 over 64. This is 1 over negative 8 quantity squared, which is 1 over 64. This is the negative of 1 over 8 squared, which is negative 1 over 64. And this is 8 squared, which is 64. Shift down a little. This is 2 to the 5th. So it's on the bottom. What we do is we put it up top, in essence. And by up top, I'm not going to write anything underneath. 2 to the positive 5, which is 32. This is 3 times 2 to the 5th, which is 3 times 32, which is 96. This is 1 over 2 times 3 squared, which is 1 over 2 times 9, which is 1 over 18. This is, so in this case, these guys just switch, right? So it becomes 2 to the 5th over 3 squared, which is 32 over 9. Let's move on. Write each of the following powers using positive exponents. Okay, so when we have a fraction and we change the exponent, if we just take the reciprocal of the fraction and then we can make the exponent positive. And that gives us 25 over 49. Again, reciprocal. Make exponent positive. And that's 16 over 81, 2 to the 4th over 3 to the 4th. Reciprocal. This is still negative. We don't change that because we're taking the reciprocal. And then when we square that, it becomes positive 25 over 36. And the negative of 3 over 2 cubed. So this says the result's going to become negative anyways, right? We're going to do this. So it's the negative of 27 over 8. Write each of the following powers with an integral base. So it wants it as an integer base. So this is 5 to the power of 1, since that's on the bottom. 5 to the negative 1. Let's remember, integral base is an integer. This is 81 to the negative 1. We could also have written this as 1 over 3 to the 4th, which would be 3 to the negative 4. This is the negative of 32 to the negative 1. We also could have written 32 as 2 to the 5th. So let's just do this down here. So it's negative 2 to the negative 5. 0.01 is 1 over 100, which is 1 over 10 squared, which is 10 to the negative 2. Negative 16 is negative 16 to the 1. We could write that as negative 4 squared. We could write that as negative 2 to the power 4. So they're powers with an integral base. So we want a base which is an integer. Okay, so that completes, or just to back up 1 second, right? I mean, it means we can't write it as, a fraction base. We need an integral base, which means we're going to need negative powers. So each of these bases is now an integer, and here we change to the fraction 1 over 100. We have the exercises, there's a recap, and all of the answers to these are shown. If you get the PDF of the answers, then there's more detailed work on some of these. The answers themselves are down here. Okay, so they're at the bottom of your worksheet. And actually, if you don't have things handy, then here's what I'm going to do. I'm going to slowly scroll through this. Well, I'll leave this here for a sec, and then you can just do little screen capture type stuff. So evaluate each of the following without the use of a calculator. This is actually all of number 1. Wait. That's all of number 1, and here's the first part of number 2. Okay, that's long enough for you to get a look at it. And then here is the second part of number 2 up through L. And scrolling down, here's the last bit of number 2. And all that's left then is the answers. But, keep in mind all of this is on Schoology. And we've got some fully worked out solutions to these, but I'm just going to fairly quickly show you them. So if you want to do any screen captures, you can.